Folks, I want to talk to you about a serious subject. Digotry. No, not bigotry, although it is a little bit the same. What we're talking about here is digotry, digital designers who discriminate against analog design. Shameful. Now, before you go telling me that's how it was in my grandpa's day, or I've always been just fine staying in the digital domain in my FPGA designs, let me stop you right there. Analog is part of everything. No matter how cool you think digital is, no matter how much you think it is a be-all, end-all of design, you really can't do much of anything without analog. Now can ya? Hi, I'm Amelia Dalton, host of Chalk Talk. In today's electronic design world, analog is an increasingly important part of just about everything we do. There is really no place for digotry anymore. Luckily, Xilinx is helping us stamp out digotry with their exciting new Agile Mixed Signal capability. My guest today is Steve Logan, and we're going to tell you about Agile Mixed Signal and how it can dramatically improve the capabilities of your next FPGA design. Before we get started, I want to remind everyone that you can click on that Download Now button below your player. There you can download a free user guide that further expands on this topic. Hi, Steve. Thank you so much for joining me today.
Thanks for having me, Amelia.
So, Steve, I'm excited to talk about analog with FPGAs today. Tell us about what we're going to discuss.
All right, so we're going to look back at a little bit of the technology evolution for Xilinx, what's going on with today's board, some of the analog and digital divide that's out there. Then we'll look at how we're tackling that with the AMS Evaluation Platform and look at the block diagrams and see what's going on inside of there. And we'll wrap it up and talk about some of the design tools that we've got and what the applications are that are best fit for AMS.
Great. So, Steve, tell us a little bit about how we got here.
All right, so Xilinx's technology evolution really started with the basic programmable logic devices. And really where we've come to these days over the last 25 or 30 years is into something that can be all programmable devices. So FPGAs, ARM processors, 3D ICs, all kinds of different things. And one of those pieces is what we call Agile Mixed Signal, which is our new integrated analog.
Okay, Xilinx is integrating all these different blocks. How does that benefit us as designers?
So we touch on a few things here with AMS in particular. So it really plays out for programmable systems integration. So you start with the basic analog building block that you integrate in, pull that off the board, and then you can do a lot of unique things along with that. It also hits on BOM cost reduction, so reducing your bill of materials as you eliminate external ADCs and analog glue components around those. Mm-hmm. And then you can increase your system performance as well by using the power of the FPGA and doing some DSP techniques and that type of thing.
All right, Steve, talk is cheap. How does this look on a real design?
All right, so on a real design board these days, as you guys know, these things are densely packed and you've got all kinds of different things going on. You might have an FPGA that's sitting at the center of the board, a big chip doing a number of different things. You might have some processors or microcontrollers that are sitting around the board as we show in the red there. And then we know that analog surrounds all these different things. You've got analog power supplies that are powering our FPGAs. You've got sensors and amplifiers and ADCs and DACs. You've got microprocessor supervisors that are sitting next to those microcontrollers and our FPGAs, making sure the voltage rails are doing what they should. You've got sequencers that, for all these different power rails, that some of them need to come up in a particular order or turn off in a particular order. So there's a lot of different things going on between analog and digital and the processor on these boards. And so really at Xilinx, we're looking at what makes sense to integrate in terms of the analog and, along with what doesn't.
Sure. So we're talking about analog with FPGAs. Aren't there a lot of times those are different designers?
They definitely are. Yeah, that's definitely been the history. You've got analog designers that are kind of doing their thing and digital designers, and these guys can be miles apart sometimes. And maybe you've got a system designer that maybe takes what the analog guy and the digital guy does and translates those together. So yeah, it's a definite challenge, but here with AMS, we're looking at how do we bridge those different design disciplines and get somebody going, whether with AMS, whether he's an analog guy or a digital guy.
Ah, I see. Okay, Steve, we've talked about this in the abstract, but what have you got in the line of boards and kits?
All right, so what we've got there we call the AMS Evaluation Platform, and it's everything you need to get started. It's the hardware, it's the reference designs, it's the tools that go along with it. So we've got a couple of photos here on this slide that really shows how that happens.
Okay.
The slide on the left there is our Kintex board, the KC705, and you've got what we call the X80C header there. That's a header connection that goes to the outside world that lets you bring in 3 analog channels. You've got some digital I/O lines. You've got 5-volt power and ground that go out to this connector that you can power up all sorts of different things.
Okay.
The first thing that we've got running here is the AMS 101 evaluation card. So that slots into this X80C header. You can drop that in and start testing some basic analog functionality. Again, remember the analog ADC portion is sitting under the fan there in our photo here on the Kintex chip. But we've got a simple little plug-in card with a DAC on it that lets you send out a simple analog sine wave signal and bring that analog back into the device integrated there.
So, Steve, you mentioned that under that fan, inside that FPGA, is some analog hardware. Tell me more about that.
All right, so what we've got inside there is what we call our 7 Series X80C block. And you've got ADCs and on-chip sensors and voltage references. So you've got a dual 12-bit, 1 megasample per second analog to digital converter. You've got 2 of them in there so you can do simultaneous sampling. So applications like motor control and 3-phase power monitoring that need those analog signals simultaneously sampled, we can do.
Okay.
And then you've also got it's truly a 16-bit digital data word that's coming out. It's linear and accurate to 12 bits.
Okay.
But you can get 16-bit performance out, and we'll look at that a bit later here. You've got on-chip thermal and power supply sensors. So that's the blue block toward the bottom left corner there. So this is an internal temperature sensor and 3 of the main voltage supply lines that we monitor inside the chip. And those are key for things like reliability, safety, and security to know that nothing funny is going on with your temperature or that your voltage supplies are still doing what you think they should be doing. So along with the on-chip sensors, we've also got the 1.25 volt internal reference there, and that's going to save you space and cost, and it's great for system monitoring applications that really need the smallest size possible. And then along with that, with those 2 ADCs, you've got a MUX, a multiplexer there that lets you get access to up to 17 external differential inputs. So for that board we were looking at earlier with all those analog parts sitting around it, you can now get access and measure those analog signals through that multiplexer and into the integrated ADCs here.
I see. Okay, so you've got the X80C block and you mentioned AMS. What is that exactly?
So AMS, or Agile Mixed Signal, is really being able to use the FPGA's signal processing capability. So doing digital signal processing kind of techniques and pulling in some of that analog glue, things like filters and op amps and that type of thing that you can do inside the FPGA. So in some ways, it's kind of the classic FPGA value proposition as far as integration goes, is being able to suck those things in that are around it. You can easily linearize temp sensors, you can filter and oversample. Mm-hmm. You can do calibration, offset and gain calibration on different signals that are out front to make sure those are as accurate as possible and do all that inside the FPGA.
So Steve, we talked about what's inside the Zinc device. What's inside the evaluation card that goes with it?
All right, so in the AMS 101 evaluation card, we've got a few things going on there. These all connect over that 20-pin X80C header that I was mentioning earlier on. The key portion on that block is a pair of 16-bit DACs from analog devices. And we have those send out a simple sine wave signal, and then an analog signal comes back across onto the FPGA or the Zinc baseboard onto a simple little reference design that can read those X80C channels. And that's running inside, running on microblaze, or in the case of Zinc, it's running on the ARM processors to be able to resolve those analog signals. And then, so with that, again, I mentioned the sine wave coming off the DACs. This is a simple little test use case that we've got, that we send out a sine wave and then digitize that signal. So what you're looking at here is what we call the AMS Evaluator GUI. And this is everything that you'd get with a discrete ADC EV kit. So you can look at these signals in the time domain or the frequency domain. You can look at the linearity of the X80C. You can look at that sensor data for the internal temp sensors or voltage sensors. And then you can debug all of that and save that data into an Excel file.
Very cool. So what else is in this AMS GUI that you've got?
So along with that, if we look at the frequency domain tab here, you can see the FFT, the fast Fourier transform of that sine wave signal. And if you look down below there, you can see a lot of the proof points that analog guys are going to be used to seeing. So you've got signal to noise ratio, you've got total harmonic distortion, things like SINAD, SFDR, and effective number of bits. So this really proves, and this is a screen capture of the XADC running right out of the box, giving you 65 dB of signal to noise ratio and about 10.5 effective number of bits. So these are the key ADC performance metrics, and we're just starting to scratch the surface here, what we can do with this. And if you look on the right, you can see a lot of the other menus and pull-down menus that you can play with: the sample rate, single channel or simultaneous sampling. You can choose to have decimation turned on or off and achieve even higher performance in that respect.
Okay. So we've talked about the proof points for the analog guys. What about the rest of us?
All right, so for the digital guys that know and love Xilinx, you've got a couple of different tools inside the ICE design suite and then moving over to Vivado here, our new design suite as well. One of those is chip scope. So what that lets you look at in the use case here, this photo that we've got, is the internal die temperature and the three main voltage supplies that we monitor. So those are VCC int and VCC aux and VCC BRAM. And you can make sure that nothing funny is going on with your power supplies. Nobody's trying to hack into your system and they're yanking the power supplies around more than they should, or that the temperature's not skyrocketing and, something shorted or something funny's going on.
Good.
So you can monitor all that inside chip scope. And then like we show here, you can also test these voltages with the AMS platform. And so that's what we've got here, where you see the VCC int dropping down and then picking back up, and the same thing with VCC aux. Along with that, we've also got what we call the XADC Wizard. This is another tool that we've got that lets you instantiate the FPGA design inside Logic Core.
Okay.
And basically what you can do is some of these same cool things of monitoring for over temperature, monitoring and setting up alarms for your voltage supplies getting too high or too low. You can set all that up. This is just one screenshot of the tool. You can set up the sample rate, a lot of different things. And then it'll give you an output block of code in a .v file, a tickle script, or a .xco file, or a few other different versions. So for the digital guys that are used to programming this way, they've got a great tool that gets them started.
Very cool. So Steve, what are people actually going to use this for?
All right, so the best applications that we've seen out there are what we generically call system monitoring. And so a lot of these are looking at voltages, currents, temperature, that kind of thing. You might also see it in some battery backup systems. Anti-tamper, I was mentioning hacking a bit earlier there, for some of the aerospace and defense kind of guys, to make sure nobody's trying to hack into the FPGA and do something funny or pulling the temperature around. And then loosely what we call security. So just as a, kind of a backup system, even if somebody's got a more accurate ADC out front, they can use this integrated ADC as a backup, just as a sanity check to make sure that everything's functioning like it should.
Okay.
It's also a good fit for things like motor control systems, so looking at those stator currents and that kind of thing. Resistive touch screens, as you see in the two images here.
So, Steve, do you have any examples of these kind of designs?
We do. We've got a couple of examples of Agile Mixed Signal in action here. These are motor control and touchscreen demos. We've got what we call the industrial drives kit with the Xilinx 7000 that'll be coming in November here. You can see from the photo in the bottom right corner there, that's running 4 Dunker motors. And you've got, in terms of just the ADC, you've got a dual measurement path that you can read it through the XADC. And those signals come across the little white cable that you can see there. These are FMC FPGA mezzanine cards that are connected in. Or you can use the onboard 16-bit ADC that's sitting on the FMC card itself. Along with that, we've also got a touchscreen FMC card. So you can see here in the bottom left corner that's hooked up with our Zinc board. A simple little resistive touchscreen that Digilent is making where you can read the X and Y coordinates using the XADC and then come in and do all your complex digital algorithms inside the FPGA for a touchscreen card. The screen capture there in the bottom right is just a simple little demo running on the Kintex board that's capturing that same data as you'd scribbled the letters XADC on the touchscreen card.
Okay. So are there any other applications you think AMS is good for?
So one of the best ones probably is generically what we'll call sensors, right? And those are things like temperature, pressure, humidity, and that kind of thing.
Okay.
So this slide here really shows a good example of that. This is one from an actual customer that was doing a resistive temperature detector, an RTD temp sensor out front. And they had a lot of analog glue around that. You had op amps, you had a DAC to come along and calibrate for some of the output offset of that op amp. You had a filter there with resistors and capacitors, an active filter with op amps. And they had a discrete ADC sitting out there next to either their microcontroller or their FPGA.
Okay.
So when you add all this up, the DAC at about $1.50, the filter with the op amp and the passives coming in somewhere around $1, and somewhere in the ballpark at $2.50 for the ADC, we can integrate all of that with the AMS technology and the x86 block in all the 7 series devices.
Very nice.
So where we can end up is just you still need the resistors out front and the RTD sensor. You still need that first op amp. But then after that, you can just have a simple little RC low-pass filter in front of the x86 and do all those DSP kind of techniques inside either the Zinc devices we show here or any of the 7 series devices, Artex, Kintex, or Vertex. So those are things like decimation, filtering, linearization, which in this case is what's going on with that temp sensor, and calibration. And since we're measuring temperature, we can oversample in the FPGA and achieve a higher accuracy and a higher SNR. So you can see that 14-bit 50 kilosample ADC up there, really with our 12-bit 1 megasample ADC and the power of oversampling, we can get the same kind of performance that this customer was looking for.
Okay, great. Steve, I am ready to get started. Where do I go for more information?
All right, the next step you want to go to really is xilinx.com/AMS. That's our page that's got all the details that you need to get started. From there, you'll be able to download these reference designs. At this point, we've got them running on Kintex and Vertex and Zinc. Very soon, we'll have the Artex as well. Once you're on that site on Xilinx's page there, you'll want to download the AMS 101 user guide, and that's user guide 886. And then you're going to want to use these tools that are inside ICE and Bravado that we've already got that are available for you to use today and get started measuring analog in your system today.
Great. I'm going there right now. Well, thank you so much for joining me today, Steve. It was a pleasure speaking with you.
Thanks again for having me.
And before we go, don't forget to click that Download Now button below the player to download a free user guide that further expands on this topic. For Chalk Talk, I'm Amelia Dalton. For more Chalk Talks, check out the on-demand section of eejournal.com.